At Fermilab, we study nature at its most fundamental, drilling down to the smallest scales of matter using some of the largest and most advanced machines in the world. Accelerators, powerful microscopes, send particles barreling at near light speed into other matter, creating subatomic scraps. Detectors zoom in on those fleeting pieces, making the invisible perceptible. And sophisticated computers sweep through all of it, crushing mountains of information into gems of data. We also use our cutting-edge technology to explore the mysteries of dark matter and the quantum realm. Thousands of scientists from around the world partner with Fermilab to explore how the universe works, expanding humanity's understanding of matter, energy, space, and time. Fermilab is solving the mysteries of the universe. At Fermilab,
thank you everyone for joining us for our next installment of Virtual Ask a Scientist. My name is Amanda Early. I work in the Office of Education and Public Engagement at Fermilab. Today, we're going to hear about the story behind one of our neutrino experiments at the lab, MicroBooNE. Our speaker, London Cooper-Troendle, is a fifth-year grad student at Yale University. He works under Professor Bonnie Fleming on the MicroBooNE experiment at Fermilab. And if you've watched some of the YouTube videos about MicroBooNE, you've probably seen Bonnie in those. So he is currently working on his dissertation on new measurements from the MicroBooNE data and hopes to graduate in the fall of this year. So London, if you want to take it away.
All right. Hi, thank you. So I'm going to be discussing the history of MicroBooNE. And so this means I'll start by just giving you an introduction to neutrinos and why we care about them, and then kind of walk through the experiments that lead up to MicroBooNE, and then finish off with talking about MicroBooNE itself, the design, and the data we look at. So to start with, we have to ask the question of what is a neutrino? And neutrinos are these very tiny particles that you can't even see, and they are very light and travel most of the time close to the speed of light, so fast that we don't even know exactly how close to the speed of light they get. We don't know if it's 99.999% or 99.999999%. And this means that it's very difficult to measure them and do anything with them, because they can go all the way through the Earth. And in fact, they can go through the Earth 100 times without even touching anything at all. So when we work with neutrinos, we deal with huge numbers of them, 10 to the 17 at a time, and we just try to see one of them. Neutrinos are not on the periodic table, so they're not atoms or part of atoms. They're not protons or neutrons or quarks or electrons. They're their own separate thing, and they're created in nuclear reactions. So the biggest example is a star, like our sun that I have here, where we have some of these ghostly neutrinos heading to the Earth and others just heading off into space. And then other places the neutrinos come from, the early universe, where similar to the cosmic microwave background, we expect to see a cosmic neutrino background. And we just haven't built detectors that are sensitive enough to detect that yet, but we're pretty confident that that exists. Additionally, they get created in radioactive decay sometimes, also in nuclear reactors, which is one of the main sources for neutrino detectors. And then finally, yes, nuclear bombs will create neutrinos. And there's actually been, I believe, some ideas thrown out that you could kind of spy on a neighboring country with a neutrino detector to try to see if they were secretly testing nuclear bombs underground, by trying to see if they have any neutrinos that are being sent over to you. So that's what they are, but why do we care? If they're these small invisible particles that never touch anything, then just leave them alone. They're not affecting us. Stop wasting time thinking about them. But I think the better answer is that they are another final frontier to physics. So if you're familiar with the show Star Trek, it always opens by talking about how space is the final frontier. And I think that in physics, there are a couple of areas that still have lots left to learn. And one of them is neutrinos. And that's because there's so much about them that we don't yet know. So for example, we don't know how how much mass they have. I mean, we know it's small, but we don't know exactly how small. And we don't even know which is heaviest. There are three different types: the electron neutrino, the muon neutrino, and the tau neutrino. And we don't even know how to order them. We also don't know if they violate charge parity symmetry or how much they violate it. And this is an important question because this could answer why we see so much matter in the universe and not antimatter, because there's largely a big symmetry between matter and antimatter, but all the things that we see basically are matter. And then finally, we know that the neutrinos oscillate between the three types, but there's a lot of the specifics there, the specific how much they oscillate, that we still need to measure more precisely. So by measuring neutrinos in experiments such as MicroBooNE, we can learn more about them and at the same time test our knowledge of the standard model of physics, which is our leading theory of how particle physics works. And neutrinos have kind of consistently bucked our expectations and gone against our intuition here. So even back to the discovery of the neutrino, or even before that, I guess the theorization of the neutrino, at one time we didn't think there was a neutrino, but then an experiment had a result that we couldn't understand. And the neutrino was hypothesized as a way to explain that uncertain measurement. And then later, we thought the neutrinos were massless, like the photons for light. But then we found out that that could not be possible, and they did have mass. So at multiple times, our understanding and intuition has not led us in the right direction. So that's why it's especially important to do these measurements and look to see whether things are the way we expect them to be. So I mentioned that neutrinos oscillate, but we need to spend a little more talking about what this even means. So there's the three flavors of neutrinos: the electron, muon, and tau. And these correspond to the three particles: the electron, the muon, and the tau. And you're all familiar with the electron, probably. Those of negative charge, and they're inside the atom. But you probably haven't heard of the muon particle or the tau particle. And I basically just want to give you the impression that they're very similar to the electron. They're kind of like the bigger, older siblings. So the muon is bigger and heavier than the electron, but otherwise pretty similar. And then the tau is even bigger and heavier. And for the neutrinos, we don't actually know which of them is the heaviest, as I mentioned before. So the oscillations between the neutrino types depend on the energy of the neutrino and also how far they've traveled. And in particular, what's really matters is that ratio, how far they've traveled divided by how much energy they have, L over E, length divided by energy. So I'll mention that later on. But when I say that we don't know the ordering of how the neutrino masses go, what it means is you could imagine something like this, where we know it goes electron, muon, tau, and you could say, well, it's probably the same in neutrinos: electron neutrino, muon neutrino, tau neutrino. And that would make sense. But it could also be like this: electron, tau, muon, or muon, electron, tau, or muon, tau, electron, or tau, muon, electron. You get the point. It could be any of these orderings, and we're not entirely sure. But the one thing we do know is that two of the neutrinos have a very similar mass, and then the third is different. But that still means that it could be one tiny neutrino and then two heavier ones, or two tiny neutrinos and one heavier one. Now keep in mind, these are all lightweight, but it's just a relative thing, much lighter versus slightly light. So when we have all these questions about neutrinos, the way to get answers is to get data. So one of the experiments back in the 90s that was trying to get data on neutrino oscillations was liquid scintillator neutrino detector. So I have an image here, not actually from LS&D, I couldn't find one, but from Super Kamiokande, which is a very similar experiment. And the idea here is you have this big sphere and you fill it with water or mineral oil, depending on the experiment. And around the edges, you put all of these photomultiplier tubes, which are kind of like light bulbs in reverse. So they, instead of taking electricity and creating a flash of light with it, like a light bulb, instead they do the reverse, where light hits them and then they turn that into an electrical signal. So they function as the eyeballs of the experiment, where we take all those electrical signals and figure out when and where the light occurred. So what happens is we shoot neutrinos through this detector, and sometimes they'll hit the water in the inside and create flashes of light. in two different ways. There's scintillation light, which is kind of like a glow in the dark, where if you put energy into something like maybe a glow in the dark sticky, then it'll continue to glow for a little bit later. And so we see that light, and also Cherenkov light, which is kind of like a sonic boom instead with light. And I'll talk about that more in just a second. So LS&D was trying to look for this oscillation from the muon neutrino to the electron neutrino, actually the antiparticles, but I don't want to get too deep into the physics and math. But it's looking for this oscillation. And what it ended up finding was that there was indeed an oscillation from muon to electron, like we at this point expected, but there was more than theory predicted. So this was an anomalous measurement of excess low energy oscillations. And this was kind of a head scratcher. So that's what gets the ball rolling towards MicroBooNE, is a series of experiments of trying to understand this excess. We're going to get back to that in a minute, but I just want to talk about this Cherenkov radiation, which is one of the main ways to see light in LS&D. And it's going to come up again in a minute. So you probably know that nothing can go faster than the speed of light in a vacuum, but there's a lot of emphasis here on the in a vacuum part, so you should really think of this as nothing can go faster than the speed of causality. And it just so happens that light can go at the speed of causality when light is in a vacuum. But these detectors, as I mentioned, they're not in a vacuum. They're in water or mineral oil. And this means that light moves slower, about 25% slower. So highly energetic particles can actually go faster than light. And what happens when you do this is something like a sonic boom. And so I have the diagram here where the neutrino comes in from the left and it hits something, and that releases a charged particle going near the speed of light. And this charged particle sends off this sonic boom-like Cherenkov radiation in a cone, and that hits the edge of the detector where all those photomultiplier tubes are, the eyeballs of the experiment, and they pick up a ring signal from the Cherenkov radiation. And that tells us there was a charged particle going really fast through the detector, which is a good indication that a neutrino or maybe something else like a cosmic ray was passing through the detector. So on the top here, there's an image from Super Kamiokande, and we can see two distinct rings, which is telling us that there were two particles created at this time. So after LS&D, the next experiment to follow up on that low energy excess and oscillations was MicroBooNE. And so this began taking data in 2002, and I think it's still taking data now. I know it was a couple of years ago. So this is an impressive run, 20 years. And MicroBooNE is trying to also look into this nu mu to nu e oscillation at a low length divided by energy ratio. But MicroBooNE's idea is to increase the energy so that we can get a better view at what's going on, because more energy means more stuff to see. And this means that it increases the length that it's measuring at to keep that ratio the same. And there's an image down here of MicroBooNE, and you can see it's pretty similar to LS&D in design. And MicroBooNE actually came out with a result that agreed with LS&D at a 4.6 sigma significance level. And what this means is there's one of three things happening, or maybe multiple at the same time. But it could be that the experiment made a mistake or a bad assumption. There's lots of professional scientists that spend years of their life trying to make sure that this result doesn't happen, but you can never be totally sure that you haven't made a mistake, so that's always a possibility. The other option is that it could just be random chance. Like if you flip 10 coins and they all get heads, that seems a little strange. And then if you flip 100 coins and they all get heads, then you're really thinking there's something wrong with my coins here. So they measured this, that's what the 4.6 sigma means. There's a 2 in a million chance that the result they got was just due to randomness or bad luck. So 2 in a million is incredibly low. So we don't think it's number 2. And if everybody did the best work they could, then we also think that it's not number 1, which leads us to think that maybe there's something that's not quite right in our standard model of physics. And so one possible explanation there would be a new particle. But we don't want to just go ahead and say there's a new particle, because what we really want is like a smoking gun, something we can really look to and point at and say it's definitely not what we expected. And the Cherenkov detector design with these rings that we measure can't quite do that. And that's because sometimes particles don't go faster than light, and then we can't see them, but they don't make Cherenkov radiation. And also, it's difficult to tell different particles apart because like different particles will make similar looking rings. And we really want to be able to say exactly what's happening and where it's happening. And these rings just aren't giving us enough information. So we need to look at a new detector design that lets us really tell what's going on in these experiments. So that brings us to the idea of bubble chambers. And bubble chambers, when a particle goes through them, they create all these tiny little bubbles along the track that the particle takes. And then a camera takes an image of these tracks of the bubbles. And what we're left with are these great images showing exactly where the particles went. So this really gives us the precision that we were looking for. So if only we could make a bubble chamber detector at the size we need to do this physics. But the problem is that bubble chambers have difficulty getting to large sizes, at least with the budgets we have going on here. So that was the real benefit of the Shrenkov detector, because they're really just this sphere filled with water or mineral oil, which is really, well, not cheap, but an acceptable price. So there's this trade-off here, the great precise pictures or the scalability to huge size. And neither of these detectors is really giving us what we want. So that's what introduces MicroBooNE and the liquid argon time projection chamber, which is a new detector type. And it really tries to be the best of both of these detector designs. So you fill these liquid argon chambers with liquid argon, which means that because liquid argon isn't terribly expensive, you can scale it to massive sizes. But then at the same time, as I'll get into more detail in a minute, you, just like the bubble chambers, you get these great images of exactly where every particle was, and you can tell what type each particle was. So it's going to hopefully give us the smoking gun that we're looking for. And then as a bonus, instead of just giving us an image, the liquid argon time projection chamber can also measure calorimetry, which means it tells us how much energy the particles were releasing into the detector at each precise location. And this is really convenient for figuring out the energy and type of the particles in the detector. So that's just another piece of the puzzle in figuring out exactly what was happening. So here we have a kind of schematic of the MicroBooNE detector. It's about the size of a bus. It's this big cylinder, and inside of it, we have the liquid argon, and on one of the walls, the wire planes. And so it's tough to really see what's going on here. But if you look closely, you might be able to see there are thousands of little wires all parallel going along the detector. And these are copper wires that are going to measure charge as the electrons pass by them. I actually was able to work on stringing up some of these wires, not on MicroBooNE, but on a different experiment, a more recent one, LS&D, I believe. So that was a fun time, rather tedious, I guess, but still fun. So before I get into the particular details, I just want to play a short clip to kind of give you a sense of what's going on. So this is kind of describe in a more fun way what it's like when a neutrino goes through a detector. So this is a scene from a Star Wars movie, The Last Jedi, I think. So here we have the neutrino goes in and boom, it hits everything and it's gone. But then the particles that it shoots out go through the rest of the detector. They hit all the argon in the detector, and what we're left with is all this debris. And so there's all our debris, and that's what we really look at seeing. We don't see the neutrino, we just see all the chaos that it creates. So in a less fun but more informative way, on the left here, we have the neutrino coming in as this purple dashed arrow, and then at some point it hits an argon atom in the detector, and the neutrino keeps going, but we're no longer interested. And off from the neutrino shoot off some charged particles like protons, or electrons, or muons, and these charged particles create all this debris in the detector. And by debris, I mean electrons. And the detector also has an electric field that pushes these electrons to the edge of the detector where those wire planes are. And as the electrons move past the wires, they create current in the wires. And then it's our job to kind of figure out, based on the current we see, that tells us which or how many electrons and where they pass by the wires at each time interval. And we can kind of do a lot of math and reconstruction work and end up with an image like on the right of what is going on. So we have the neutrino beam coming in from the left. It hits here at the red dot, and then offshoots, it looks like 4 particles as well as one shower here, which is tougher to describe, but this is an electron shower. And then you can also see there are some cosmic ray muons going through the detector. And what's happening here is these muons are not at the same location. but we're kind of getting a projected view. So it's kind of like if you put your fingers over top of each other, but then give them some space. If you just look at it with one eye, it kind of looks like your fingers are touching each other, but you really know that they're not. It's just that that's just the projected view. So this line here, I think, is not related to our neutrino. It's just the imaging issue. So what this means is that the MicroBooNE is able to try to resolve this anomaly that we've been looking at since the 90s. So originally LS&D found an anomalous low energy excess, and then MiniBooNE also agreed and confirmed the low energy excess, but couldn't really say exactly what the cause was. And now MicroBooNE is going to try to clarify exactly what is going on. Because if we see a lot of electron excess, that indicates that there are electron neutrinos creating this electron excess. But if we see photon excess, which would have a similar signature in MiniBooNE, but MicroBooNE will be able to tell the difference, then that suggests something else is going on. Perhaps interesting, but probably not a nu mu to nu e oscillation. So this is the MicroBooNE detector before it's covered in some insulation material that helps it keep cold. And in addition to resolving this big ticket question, MicroBooNE is also going to answer some other questions of ours about the properties of neutrinos that we still don't understand. And additionally, MicroBooNE is the first large-scale liquid argon time projection chamber, but it's not the last. It's now kind of spurred off this massive program of the short baseline neutrino detectors and the deep underground neutrino experiment. They're going to be built in the next decade, and it's going to cost billions of dollars. So it's a whole opening field of liquid argon time projection chambers. And MicroBooNE is really pioneering the field so that we can get the technology down. And whatever mistakes we make in MicroBooNE, we can learn from and correct in the future experiments so that they can be even better. So here we have some pictures from inside of MicroBooNE. On the right, the detector is hiding underneath of these panels that are actually trying to detect cosmic rays for us. More on the cosmic rays in a minute. And then on the left, we have a view from underneath with some of the electronics that are used to convert the charge on the wires into measurements of the actual electrons of when and where they were. And then if we step outside, we can get a view of part of the booster neutrino beam. So the about 500 meters off screen to the right, the neutrinos are created and sent in. And first they go through MicroBooNE, and then they go through this mound of Earth, which actually holds MiniBooNE. And then they go through Icarus and keep going. And there are some other experiments along the beam line, but they're out of picture. And then we get a closer view of the liquid argon test facility, which is where MicroBooNE is stored.
We do have a few questions coming in if you want to pause for those.
Oh,
or do you...
sure. It's a great time.
Okay, sure. So Colin is asking, what does the sigma significance mean?
So, yeah, here we are. So this gets into statistics. There's the normal distribution, and what we're saying is that a measurement, so basically we expect a measurement to occur along this normal distribution of events. So there's like a central value that we expect it to most likely be, but it could be a little more or less. And then as you get further more or less, it gets even more and more unlikely that you would have such an extreme measurement. And 1 sigma is like the standard measuring distance that we use, but it's not very precise. I think 2 in a million is a more precise way of saying it for this sigma value, but it's basically just telling you how rare the event is. And I guess I could talk about the precise math that lets you do that conversion, but it gets a little complicated. So I'll just say that based on this measurement and significance, an analogous way of stating it is the probability chance, 2 in a million.
And then Brandon is asking, what is low energy excess?
So the booster neutrino beam that, let's see if we can, skip ahead. The booster neutrino beam creates neutrinos at a whole range of energies. Some of them are low energy, some of them are a little higher energy. But what we're seeing is that the oscillation from the muon neutrinos that we start with to the electron neutrinos that we end up seeing, there's more oscillation than we expect to see, but only in the region of low energy neutrinos. So the high energy neutrinos do what we expect. But the low energy neutrinos, we think what's happening is that more of them are oscillating than we expect. And so that's the hint that maybe there's a new particle, like a sterile neutrino, that could help explain that anomalous measurement.
And Neil's asking, are all three known types of neutrinos detectable in the time projection chambers, and are they distinguishable?
Yes, so I believe the answer to all of that is yes. So here I kind of told you that this was an electron shower, and I didn't really go into the details. I think, well, I guess I can do it now. So electrons have this feature where they can, inside of the liquid argon, they can convert into multiple photons of light, and then those photons can actually convert back into electrons and positrons. And what this means is that the electrons kind of hop in and out of existence, or in and out of our ability to see them, because when they're just photons of light, we don't see them in the detector. So we see like an electron and then a gap, and then an electron and a gap. And what that tells us is that this is an electron and not, for example, a muon, which doesn't do this. So we can tell the difference between electrons and muons in this way. And in a more complicated way, I think we can also tell the difference between muons and taus. And all of them will show up in the detector. So the only reason we don't see taus is because the booster neutrino beam doesn't create many tau neutrinos. But I think in the DUNE experiment, because it's higher energy, I think there may be more tau neutrinos that show up that we can detect.
All right, and then the last question, and we'll move on, and we can always come back to some of these, is how is the neutrino beam created?
Right. I don't know all the particulars, but so we start off with an accelerator that takes protons and gets them going really fast. And then eventually it shoots them at a target of just some block of metal. And that creates a bunch of debris, kind of like what's going on here. And this debris is really going, because it's so fast, it's all going in the same direction that the proton was coming in from. And these debris includes some stuff like pions and kaons, and these particles decay into multiple things, but in particular neutrinos. So then if you send it through some dirt, a couple meters of dirt, everything else kind of hits the dirt and stops, but the neutrinos keep going. And what you're left with is a pretty pure beam of just neutrinos. So it's basically protons hitting things and then those things decaying into neutrinos. And they all keep going because of the momentum that the proton had initially.
Awesome. And like I said, if you want to go on, we can come back to some of the other questions later.
All right. I think I was here. So the next part, we're getting into the last section of the talk where I'm going to talk about one of the big challenges that MicroBooNE faced that was new and not a problem for the previous experiments, and then all the different tools that MicroBooNE has used to try to deal with it. And so this is kind of at the heart of science, of going into new problems, expected or unexpected, and then using your creativity to come up with solutions to those problems as they arise. So the problem here is cosmic rays, which you may or may not know anything about. Basically, protons from all over the universe created in supernova, quasars, all kinds of astrophysics events. They just fly around the universe, and some of them make them to Earth. And when they hit the upper atmosphere, they do the same thing where they bump into atoms and create a whole mess of particles. And in particular, some of the particles they create are muons. And because the atmosphere is mostly just air, the muons can just, we've got some thunder going on. We've got some, the muons pass through the air and make it all the way to the ground. And they can get inside of our detectors and mess with our images. But they also don't just affect physics experiments, they affect all kinds of things in the real world. So there's a famous example of Prius cars that were randomly accelerating, and actually this is pretty dangerous. They were getting into some crashes, and I think there were a number of injuries from this. And at first we didn't know what was going on, but it eventually came out that the problem was that these cosmic ray muons were hitting the computers in the cars and flipping a bit in the computer, and the computer got confused and thought that it should have the gas pedal on, and the driver was unable to tell the computer otherwise. And basically, this was a huge problem for Toyota, and they had to spend over $1 billion in lawsuits, and they recalled 14 million cars. So it was a huge issue, all created by cosmic rays. What an unlikely culprit. Another example of cosmic rays, you might not even be aware that this is a thing, but some people play video games and speed run them. So the goal is to go through the video game as fast as possible. It's like a race against time. And so in these speed runs, every second counts. And there was one speed run of Super Mario 64 where in the middle, Mario kind of just glitched and teleported to the top of the level. And this kind of looks like maybe the person was hacking the game. You know, they put in some of their own cheat code and were trying to skip the level. But after looking through it as much as they could, they decided the most likely culprit was that a neutrino or a cosmic ray came in and flipped a bit on the height of Mario and inadvertently helped out the speedrun. So that's just some of the ways that cosmic rays affect the real world. And in MicroBooNE, they show up all the time as these straight line tracks, these rays going through the detector. So in this detector, here's a cosmic ray, here's a cosmic ray, here's one, but then this here in purple is a neutrino. And so our job becomes to tell the difference between these cosmic rays and the neutrinos, because we don't want to falsely identify these cosmic rays as neutrinos. And there's actually about 200 cosmic rays for every neutrino in our detector, which means that we need to be over 99% accurate if we want to end up with a sample of mostly neutrinos and not actually cosmic rays that we're not interested in. So this is a very difficult problem to tackle. So one of the ways that we try to address this is by thinking back to LS&D and MicroBooNE, where they didn't have this issue. And the reason was that those experiments were using flashes of light to measure neutrinos going through the detectors. And light is very fast, which means that the delay between the interaction and the measurement is almost nothing. But instead, MicroBooNE is measuring charge, and the charge slowly drifts to the edge of the detector. And this means it's kind of like a camera with a long exposure time, where you kind of have to leave the lens open and just let the light reach the camera over a number of seconds. Well, that's what's happening for MicroBooNE, except with electrons. And while we've left our camera, if you will, open, we're not just getting the neutrino electrons, we're getting the cosmic ray electrons. So what we want to do is use the light flashes instead of the charge to determine whether something is a cosmic ray or a neutrino. Now, MicroBooNE also has some of those photo multiplier tubes like MicroBooNE and LS&D had. And so we do measure the neutrino light flash, but we still need to pair it up to the charge that we measure in the detector. So we have this technique where we predict what light we expect to see on the photomultiplier tubes, and that's in green here, with the circles kind of indicating how much light at each tube. And then in red, we have the actual measurement of the light, and we go through each cluster at a time and try to pair up the flash to the cluster. So I've just selected out this one cluster in blue here to do the comparison against, but this is happening for dozens of them all at the same time. And another way that we try to get rid of cosmic rays is by determining the directionality of a particle. So this image in the top right, it looks like either it could be a neutrino that started in the detector and then headed out, or well, like a muon from a neutrino, or it could be a cosmic ray or some other particle that started outside the detector and then came in and then came to a stop inside the detector. By just from this image, we don't know which, so we can't get rid of it. We can't rule it out. However, if we were able to figure out how much energy the particle deposited along its track, we can look for this physics thing called a Bragg peak, where as the particle comes to rest and stops moving, at the very end, the energy it deposits with this black line here, it really spikes up just at the very end. So we came up with this technique to assign a trajectory to the particle as it goes through the detector. And for a straight line track, it's pretty easy to tell what the trajectory is, but these can get more complicated. And once we have this trajectory, we're able to measure this dq dx, this charge deposition or energy deposition rate, and really spot these Bragg peaks. And that will tell us that this is in fact stopping in the detector, which means it's probably not a neutrino that we're interested in. And the last technique is machine learning. And so this is a huge field, and I won't get too detailed into it, but the idea here is that you as a human can probably look at what's going on here and tell which is neutrino and which is not. So we've got this sample neutrino interaction here, and I picked one that looked like the letter nu because that's a good first way to kind of tell nu for neutrino. And then we've got these images here. And in fact, if you want to go ahead and guess which of these images might be neutrinos, I guess I could verify for you. So I guess I'll give it a second, and then I can't see the chat. So maybe if anyone gives a guess, let me know.
So we have, Brandon says A1, Neil says 2, 3, and 3, 1.
Okay, so I think we had some good guesses there. This with Neil.
3 and 3 from
3.
Emerson.
So I haven't told you what to. I haven't told you a lot. So at our first guess, it's kind of difficult to tell. But you can imagine the machine learning is going to have thousands of images to look at. So it's got some more time to learn. But what's actually the truth here is that the 3 in green are neutrinos, the 2 in red are not neutrinos, and obviously the cars are not neutrinos. But basically what's happening is, a good way to tell is if we have this split off with stuff going in multiple directions, that's a good indicator that you have a neutrino. So you see that in the bottom left, and you see there's a split here in the middle, and then multiple tracks coming out from a starting point in the right. And then these other 2, they look like just cosmic rays because they're just a single straight line. But basically, we can use ideas like this, and the machine learning is we don't even tell them what to look for, but the neural network algorithms can figure out all on their own what to look for exactly and try to determine what's a neutrino and what's not. So this is a kind of a cheeky question. Is 99.9% an A? So basically, all of these algorithms, some of them I mentioned, some of them I didn't, were able to remove 99.9% of cosmic rays, which is a huge percentage. But that's just enough to get us to 80% of the remaining things that we see are neutrinos. There's still 20% that aren't neutrinos. So that just tells you that the initial problem we were dealing with was a huge number of cosmic rays. And at the same time, we've also misidentified some neutrinos as cosmic rays. So we end up losing about 20% of our neutrinos, but that's an acceptable loss. And what we're left with is, this is the kind of plot we might show at a talk. And the blue is what we're really looking for. And it's showing you of all the different energies of the neutrinos, here's how many of each type there are. So the blue are the stuff we want. And then the other colors are things like cosmic rays or neutrinos that are from outside the experiment. So we can't really see all of them, and we don't really want to count them. But the fact that most of what's going on here is blue is telling us that we've done a good job. And what we're left with is mostly data. So I only have 2 or 3 slides left. So maybe I'll quickly go through what in data we see. So here's an example of a neutrino interaction. And these red lines I have not applied. These are coming from our software. And that means our software is able to identify that there's an electron headed this way and a proton going this way. And I actually want to show you another example in 3D. So I'll take this link. And you can actually, I'll put it in chat. If you want, you can try to play along as well. While I'm sharing, I don't think I can get to chat. So I'll do that in a minute. But first, I'll just show you. So this is a view of the detector. And so it's this box shape is the whole detector. And here we've isolated one particle. This is a neutrino. And what it looks like happening is the neutrino is starting here. And then we have a muon heading to the left and then it looks like a pion heading down and then branching off to the right. And so we can actually, if I couldn't tell myself, I could ask the software, what do you think happened? And click these boxes and it'll tell me where it thinks everything went. And it says there's another pion. Oh, we can't see it. So this is the power of being in 3D, is we can actually look around and see exactly what's going on. So I think this software is really cool. And additionally, we can also bring in the charge. So the blue line here is kind of this trajectory that we have artificially assigned, but the red is the actual electrons that we see. And there's this gap here because some of our wires don't work, but we're able to notice that and just kind of connect the dots on the edges. But you can see, so the electrons that we initially saw, and then the trajectories that we assigned, and then the top level of like, here's a muon going this way and a pion going this way, for example. So I thought this software is really neat to be able to visualize exactly what's going on in the detector. And so my last slide is just describing where we're headed in the future. So MicroBooNE has been a huge success at demonstrating the power of the liquid argon time projection chamber. And that's given us the confidence to go ahead with the DUNE experiment and short baseline neutrino program. So these are now under construction and coming soon. And at the same time, MicroBooNE has put out a number of papers and there are more coming. And very soon, and maybe in the next couple of months, we'll be giving our first results on this low energy excess to say whether there is in fact more oscillations from muon neutrinos to electron neutrinos than we expected. And that would really kick off the precise search for perhaps a new particle. So that's very exciting times coming up. So that's the end of the talk I have.
Awesome.
There are other questions?
Yeah, there's a few more that I can go back to. Miller Jackson is asking, would you mind repeating why calculations can't be based on the Cherenkov rings? I would assume that if the rings were overlapping, they would have some effect on their measurements, which could be translated into information about the neutrinos.
Right. So yeah, so even when the rings are overlapping, so that's kind of telling us there's two particles heading in a similar direction. And you're right, that does give us some information about the neutrinos. The problem is that it's just not as precise of information. Like, which of these particles was created first? Maybe one of them was created and then it decayed into the other, or vice versa, or maybe they're created at the same time, and we don't know. And also, like, what are these particles? Are they muons or protons or electrons? And sometimes we can tell the difference, but sometimes we can't. And like protons, for example, usually don't go faster than the speed of light in the water or mineral oil. So we don't see them at all. Like, there could be a third ring here that we can't see. I mean, not a ring, like a proton, but there's no Cherenkov radiation. So those are some of the problems that this detector type comes up or deals with.
Awesome. And then Segar is asking, how much time after a collision does it take to go through the massive data and confirm neutrino? I assume it is not instantaneous.
Okay. So first I'll say that we take data for a few milliseconds, but then we have to, though, analyze that data, and the code can analyze this data pretty quickly. That's not the problem. It's creating the code and making sure that our programs are working well the way we expect and no bugs, all that kind of stuff, and that takes years. So MicroBooNE started taking data in 2015, and we're just now getting to publishing our first big result. So I guess that tells you 6 years.
And then I think a kind of a nice follow-up to that is, are there any citizen science operations where people can classify neutrino interactions? Sounds like it could be a fun thing and it could help maybe researchers sift through data.
Yeah. So it's kind of like doing the machine learning, except humans are also good at this kind of just learning. I don't know of any programs that use this. So usually what we do, I guess the reason is that scientists are very concerned about having their results be like reproducible and well understood, and like maybe there's some bias that humans are inputting, and we want to be able to measure that. So it's very easy to figure out, like to quantify the problems the machines are putting in, like if the machine has a bias in its characterization. But if we're using people, it can get tougher to do this, especially if a different person's working for every 50 images or something. So I think between that and the fact that sometimes the scientists themselves will kind of play this game of trying to tell the difference, and the scientists just have more experience, more time spent on it, and the physics knowledge to kind of know what to look for, that usually has a better chance of working out well. And we're only looking at maybe 50 images at a time. So that's the kind of scale that just the direct researchers can handle on their own. So yeah, I don't know if any open to the public, but on a totally unrelated, you might have heard of protein folding. And there was actually a game released a decade ago where you could try to fold proteins, just like a fun puzzle game. And then what would happen would be that the best examples there, the people that folded the proteins, like the people who got the best of the game, they would kind of vote on, I think you could fold a protein like this. Like, we don't know it to be true, but my intuition says this is true. And then the researchers went out and tried those best guesses, and a couple of them came out to be right. So the people playing the game kind of led the discovery. So I thought that's kind of what you're asking in a spirit, if not the particulars.
Awesome. We have a question from Colin, who, if I'm remembering right, is one of our former Saturday morning physics students. What levels of math are used in these neutrino experiments?
That's a great question. So I think there's two ways to discuss this. One is like the barrier to entry, and then the other is where you can go with it. So the barrier to entry is that if you want to be a physicist on these experiments, it's going to really help to have some knowledge of things like calculus, and then a basic understanding of maybe linear algebra. But you can kind of get away with not knowing a ton, but it will limit what you can do. But then there are a lot of different maths that do get used, and not every person will work on them. But if you know those maths and want to jump into those topics, go for it. And these mean things like linear algebra is huge in many different steps, but particularly, actually I've gone the wrong direction. Yeah, in going from these wire signals to figuring out these images, this is a ton of linear algebra. And then there's also graph theory in assigning the trajectory along the particle tracks, which, here. So this looks like kind of a simple thing to do by hand, but there's actually a lot of graph theory math going on there. Of course, calculus, statistics is huge. So you might not think of that as math, but I do. And that's, any science is going to need some statistics. Those are the ones that come to mind.
Awesome. And then back from a little bit earlier, Neil was asking, why is it that a large bubble chamber would be more expensive than a large liquid argon time projection chamber?
Yeah, I don't know the particulars. It might just be that, like, per cubic meter, bubble chambers are expensive or something. And then when you dealt with LSND, getting back to our bubble chambers. Yeah, when you dealt with LSND, because it had a low distance, remember that length per energy was the same between LSND and MicroBooNE, but MicroBooNE had more energy and therefore it needed more distance. So at a closer distance, you can think of a neutrino beam as like a flashlight, not like a laser. And a flashlight spreads the light out as it goes. So when you're really close to the flashlight, like LSND was at a short distance, you get all of that light. But the further you go away, the less light you get. And that means if you want to get the same amount of stuff going on, you need a bigger detector. So that's why MicroBooNE and MicroBooNE have to be bigger, even though the name says mini. So LSND was able to be a small experiment because it was at low energy and low distance. And then that just meant that even though bubble chambers are expensive, a small bubble chamber is not prohibitively expensive. I don't know the particulars.
All right, and then one question before we get to the virtual tour and introducing our panelists. Oh no, now I've lost it. Would you distinguish, and I'm probably going to say this wrong, Dirac or Majorana nature of neutrino and the results of MicroBooNE?
I don't think MicroBooNE can tell the difference whether we're dealing with Dirac or Majorana. Dune might be able to answer that question. I'm not sure, but I'm pretty sure that MicroBooNE isn't looking at that. I think you would need to look at, well, I guess it's tough to get into the particulars, but I think this is asking the question of whether a neutrino is its own antiparticle.
Yes.
So,
yeah.
Yeah. And I don't think we were set up to answer that.
Yeah, and Kevin, who's going to be one of our panelists, and said we could talk about that in the Q&A a little bit too. So,
oh, great. Yeah.
And then, so we'll wrap up with Gage's question. You mentioned in passing the concept of the stereoneutrino. I was wondering if there are any experiments currently in the works to try and detect these, or if there are any active projects.
Well, direct detection of a stereoneutrino seems difficult. I guess I should have mentioned some of this. Basically, in physics, we have the strong force, the weak force, electromagnetism, and gravity. And in particular, neutrinos, the three that we deal with and know exist, they only interact through the weak force. And okay, technically gravity, but that's so light that doesn't really matter. So sterile neutrinos, they get the name sterile because they don't interact through the weak force. So they don't really interact at all. Direct detection of a sterile neutrino seems just about impossible from my knowledge. So what we kind of, what you have to look for is like things like if you see excess muon to electron oscillations, and your best or only explanation for how could that come about might be a sterile neutrino. But it's an indirect method.
Awesome, and thank you so much for this great talk. I loved the Star Wars analogy, and but thank you so much. And if you want to stick around, if people have more questions, if you have time, London, if you don't mind answering them in the chat as we move on to the next section.
Okay.
Awesome, thank you very, very much. This is great. And so for the next part of Ask a Scientist, we do have a virtual tour, but I'm going to rely on some of our panelists to explain some of the things that we're seeing here. So I'm going to have them introduce themselves and the work that they do before I share my screen and get to that. So just going in the order that I see you on Zoom, we have Kevin Kelly with us.
Hi, I'm Kevin. I'm a theoretical particle physicist. I'm a postdoctoral researcher in the theory group at Fermilab. I like to study things, obviously, like neutrinos, dark matter, the possibility that those puzzles are related, and how we can learn more about them.
Awesome. And we have Lauren Yates.
Hi, I'm Lauren. I'm a grad student working on MicroBooNE along with London.
Awesome. And we have Samantha Sword-Felberg.
Hi, I'm a grad student also working on MicroBooNE with London and Lauren.
And we also have Sophie Berkman.
Hi, I'm Sophie. I'm a postdoc at Fermilab. I work on MicroBooNE with Lauren and Samantha, and I did my PhD on Super Kamiokande, so I can also answer questions about Cherenkov detectors.
Awesome, and thank you all for being here. And after a super long time of not actually seeing all of you, it's really nice to see you on Zoom. Yeah. So what I've put together is we had some lab staff go on site for us and take some pictures of the Neutrino campus and also the the inside of the building that has the MicroBooNE detector. So they're not here, but Cindy, Joe, and Rob Fine took some fantastic pictures that I put together into a virtual tour using GatherTown. So we've got our kind of the Wilson Hall is kind of where everyone knows. If you've been to Fermilab, it's the iconic high rise. It's the building behind me. It's the building behind Lauren. And so if we zoom out, if you haven't been to Fermilab, it's a huge campus. I don't even have it all captured on here. It's a 6,800 acre site. So Wilson Hall kind of being our starting point when you're talking about the accelerator process and how we get the neutrinos. We've got our Tevatron ring. So a lot of people think of the Tevatron when they hear of Fermilab, you know, responsible CDF and D0 for the discovery of the top quark. It was turned off when the LHC came online. And so now our accelerators that we use for our neutrino experiments use the booster and also the main injector ring. So this is just kind of an overview of the campus. And over here is our neutrino campus, where we have some of those buildings that London was showing you in his talk. So as we go through, I have just this short animation to kind of show everyone what the accelerators are doing and how we're getting beam to our experiments. So that kind of shows you where the neutrino beams are coming from. You know, we're talking about the low energy with MicroBooNE. They're coming from the booster. And if I take my little virtual tourist here, and to kind of give you an overview. So if you look to, if you're going to go down this road, Geese Road here, it makes me miss campus so much. I'm going to say that too. And you look down this road, this is where you're going to see our short baseline near detector. And so that is part of the experiment, the short baseline neutrino program that London was talking about. That's got 3 detectors, a short baseline near detector. So this is the one that's closest to the target. And does anyone work on this particular one? I know it's going to have, you know, we're going to get a lot of neutrinos because it's like, what was it, 110 meters from the booster target. And so we're going to be able to get a lot of statistical measurements on those first batch of neutrinos that are going through the short baseline program. And then if you turn and you go the other way, and this is always when I'm driving around campus where I start questioning if I'm in the right spot. And you look down and you can see the building where the MicroBooNE detector is housed. And then you've got the other neutrino detectors down this way. So we're going to skip over MicroBooNE for just a minute. And we're going to go down to where the FAR detector is in the short baseline program. And that building looks very similar to the near detector building. This is the where the Icarus detector is housed. Icarus came from Italy. It was refurbished over at CERN. And this then was put on a ship and sent to us. So all the way from Italy. And I think if you still look up the hashtag Icarus trip, you can kind of relive that journey. And I remember when I was watching on a map as it was getting closer, because my office is up on the 15th floor. So I was hoping to look out and be able to see it come as it drove onto campus. It was pretty cool. And then in one of our previous talks, we talked about this building here. This is where we have our neutrino experiments that are 300 feet underground, where we have NOVA that sends neutrinos to Minnesota. And actually, this is all looking totally different. Like if you go down here, these detectors down here at the end aren't being used anymore. We're actually going to repurpose this space. So it's really cool and still exciting times and new projects getting up and running at the lab. So if we go back to where we were with MicroBooNE, and here's where I'm going to start relying on some of our panelists to explain what we're seeing. So this is the building, and London showed you what the detector looked like. So when the detector was installed, they actually came in through the roof. I always love when you can kind of see people for reference. So when he says it's about the size of a school bus, he wasn't exaggerating. And now when you go inside the building, if only I could scale buildings like that in real life. This is what you see when you kind of walk in. If you look back towards the door, and again, these pictures are all from Cindy, Joe, and Rob Fine. They're pretty great. Lauren, is anything you want to talk to us about with what we're seeing kind of over here on the right? And I think we can get a little picture of a crane up here too.
I actually don't know what is on the right there. I don't know if Samantha or London or Sophie do. It looks like part of the cryo system, maybe.
I think it was part of the initial portion of the cryo system, but that's the tale that's been passed down throughout generations of grad students.
Yeah.
So.
Yeah, yes, that's what I've heard also.
Yeah.
Awesome. And then, so then we can talk a little bit about, if you scan over a little bit more, and you can see the orange sign that was hanging on the detector as it was being lowered into the building, but this is the cosmic ray shielding. So the detector is actually under this. So Samantha, do you want to talk a little bit about
Yeah,
why we need to have, I mean, I know London talked about it too, but just to kind of reiterate it.
Yeah, of course. So our detector is not, so London talked about, or Amanda actually just mentioned the experiments that are further down on Neutrino campus that are further down below the ground. And in those instances, the reason you want to do that is because you're trying to limit a background known as cosmic rays. And cosmic rays, they tend to be you tend to be shielded from them the further down you go into the ground. So the dirt basically helps you. But with MicroBooNE, we are what is called an on-surface detector. So when we are looking at images, we tend to be plagued by cosmics a lot. So in an effort to fix that, what we did is we placed panels that you see obviously in this picture here. They're placed on the top. I think there's one on the bottom, and then there's some on the sides. And the idea is that when a muon, or that cosmic ray, which is the high energy muon, comes in, we can tag it with this cosmic ray tagger. And then if it exits our detector, we can then create a trajectory between those 2 points. And that tells us, okay, that's a cosmic ray. It's not in time with our beam. It's a background, and then we can remove it in post-processing.
Awesome, thank you. And then if we go, we can go back here as if we're walking around and face the front again. And so again, you're seeing that shielding and all this piping over here. Is that part of the cryo system, Sophie?
Yes, so that's where, so the pipes along the side is where the argon that's stored outside the building enters the building, and then it comes in and goes around and then down into this white thing, which is the phase separator. And this cool is part of what is cooling the argon, mixing it with the liquid nitrogen to make it basically liquid. And so when we fill the detector, we have to add additional argon from the outside. And that comes in through these pipes that you're seeing here and then down into the detector. And the reason that we have to fill the detector sometimes is because basically because of this constant circulation, and it's not exactly closed, but we fill pretty infrequently these days, sort of every 3 months. We used to fill more frequently when we were analyzing the argon continuously, but we found that those readings were not necessary, and our detector itself was a better measure of the argon purity than the gas analyzers that could tell us the ppm of different contaminants.
Awesome. Thank you. And then so going down a little bit further. So if you were to look underneath, if you could get down under, and you can, and we've got some video of that too, which is kind of cool because I've actually never seen that. So this is kind of the end of the detector, correct? It's got some kind of insulation around it. You can see that cosmic ray shielding there. And so if you could get underneath, and then I have a short video of actually what it looks like kind of standing down there and looking around. So this is the platform kind of that we were looking at from the start. I've never looked over the railing. I didn't realize how far down that, I mean, like, I know how big the detector is, but looking down and then looking up gives you a totally different perspective. And then one other part that I wanted to show you before we get to questions is there's actually an app that you can download that takes you inside the kind of a simulated virtual version of the MicroBooNE detector to see, kind of give you the best version of what you would see if you were standing inside, which is clearly something you can't actually do. So this is, I can put the link to this in the chat after we're done. And these are the photo multiplier tubes. Is that what's represented there?
Yes.
And then with the purple lines, what are those showing?
I believe those are cosmic ray tracks. So muons that are coming from the sky.
Cool. So, and it's pretty cool. I wasn't going to try to manage, you have to use this on your phone, so I wasn't going to try to manage sharing my phone screen and trying to do this, but they have a game where you can practice identifying like different neutrino tracks, and you can see actual events and simulated events, kind of what we're looking at right now. So I'll make sure I'll put that in the chat. But if we could see inside, this is kind of a version of what we might be able to look at. And with that, we'll start taking some questions. So if we want to go back, Kevin, to again, I'm probably saying this wrong, Majorana neutrinos and Dirac, if you want to talk a little bit about that.
Yeah, it's okay not knowing how to pronounce it. I think if you ask 3 different theoretical physicists how to pronounce it, you'll get 5 different answers.
Okay.
The idea behind those 2 types of neutrinos are whether or not neutrinos are their own antiparticles. Some of the particles that London talked about throughout the talk, for instance, muons and electrons, he also talked about their positively charged counterparts. So an electron's positively charged counterpart we call a positron. It's the exact same as the electron, just has the opposite charge. Those are antiparticles. We know in our standard model of particle physics that every particle has an antiparticle, but neutrinos are special in that of the standard model particles, things like quarks, electrons, muons, and neutrinos, they're the only ones that we know of that are, they make up matter and they are neutral. They don't have any charge. And so they're the only ones that could possibly have this special feature of being their own antiparticle. The reason that we're also pretty excited about this possibility is it has some connections to some of the things that London talked about. For instance, in the early universe, we think that there was equal amounts of particles and antiparticles floating about in this early universe plasma. And now we're all made out of matter. I don't have any positrons in my body. I don't think so. And so if neutrinos are these Majorana particles, then there's a possibility that that is part of why we have matter today and not antimatter. Now, the difficulty in actually figuring this out comes in the fact that neutrinos are very, 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 very light. And so any sort of effect you could look for in an experiment to figure out whether they're Dirac or Majorana, it's suppressed by this fact that neutrinos have very little mass. And so experiments like MicroBooNE or even DUNE aren't necessarily the best place to try to figure this out. There are experiments that are kind of dedicated for this. They go under the name of neutrinoless double beta decay experiments. They're looking for this super rare process where an atom violates this thing called lepton number and it spits out 2 electrons and nothing else all at once. And that can only happen if neutrinos are Majorana particles. And those are really right now our best bet at figuring out what type these neutrinos are.
Awesome, thank you. So a question that someone sent to me was, why liquid argon? Lauren, do you want to take that one?
Sure. So liquid argon, to have a detector like this work where you have a time projection chamber, you really need to be working with a noble element. You need to work with something where like the electrons can be ionized and then propagate through like a couple meters or more without getting eaten by other atoms, which is not really possible in anything other than a noble element. So for, then you can kind of go down your periodic table, which we'll see how good my memory is, but dense is good. So the farther you can get down the periodic table, like in rows, the better. Radioactive is bad. So like radon is not a good choice. Xenon in principle can work, but liquid xenon is really, really, really expensive. Whereas argon makes up, I'm gonna blank on the number, but several percent of the air that we breathe. So you can actually just pull argon out of the air and turn it into a liquid. And that makes liquid argon relatively quite affordable compared to the other liquid nobles. And that's pretty much why. I don't know if other people want to add to that, but that's.
Can I add one thing, please, Lauren? I think that was a great explanation. I just wanted to say that the final reason is that you can use liquid nitrogen to get argon to be a liquid, because basically the point at which argon becomes liquid is just slightly above the point at which nitrogen is liquid. And so this makes it possible to cool the argon with liquid nitrogen, which is also a very common and possible technique to use.
As far as
so that enables the detectors as well.
Yeah.
From a technical standpoint.
Awesome.
That's a good point too.
Portable
cryogenics, always good.
So I wonder if each of you can talk a little bit about the work you've done on MicroBooNE. You know, we had this talk and we have seen the detector. So, and I know everyone works on different things. So Samantha, do you want to talk a little bit about what you work on specifically?
Sure, yeah. So London mentioned a lot about neutrino oscillations, and the importance of understanding these oscillations leads to figuring out different things about neutrinos. Now, in order to calculate oscillations, you have to know something called a cross-section. So what is the probability that a neutrino is going to interact with an argon atom and produce bleh event, essentially? And so I work basically on cross-sections, and the idea is that the cross-section will change depending upon what's happening in the nucleus, you know, how the neutrinos feel in that day. Like there's all sorts of things that can change the cross-section. And so I study more of the nuclear effects that happen in argon, which is it's a dense nucleus, as we've said. It's a nucleus that not a lot of people have studied up to this point in terms of certain nuclear effects. And so I'm trying to characterize those events such that when we go to make our predictions on oscillation parameters, they're much more accurate because we know what the cross-section will be. I also work as a chime projection high voltage expert. So basically getting the power to our experiment. To give you an idea, our experiment runs to actually create the electric field that we use to drift the electrons. It's set at about 70,000 volts, which, to give you a scale, your cell phone charger is about 100 volts. So that's a huge multiplier. And so when you're dealing with that kind of like voltage, you can't just turn the detector off. Like there's no light switch for that. So you have to be very careful turning off the detector, turning it back on. And so those are kind of the things that I do in MicroBooNE right now.
Awesome. Lauren, do you want to go next?
Sure. So I am primarily working on, I missed parts of London's talk, but we talked about this, searching for electron neutrinos in the MicroBooNE detector, and whether we're seeing more of those than we might expect from the boosted neutrino beam, similar to what MiniBooNE saw. So that has sort of been my thesis analysis. One of the things that I worked on in particular is actually not just like measuring the electron neutrinos, but trying to figure out, like, from a statistic sense, or from a probability sense, how compatible or incompatible is that observation with different predictions? Basically answering how well can we measure what we measure, something we call systematic uncertainties. So that's kind of been my jam. I also work as a on-call PMT expert, as an expert for the PMT subsystem in the detector.
Awesome. And Sophie?
Oh, yeah. So I work on, as Lauren mentioned, I work on a similar complementary analysis, also looking for this low energy excess that London discussed. And I've worked on a broad range of topics in this analysis, but my main focus was on developing a method to identify electron neutrinos that don't have any hadronic activity associated. So that means that they don't have the V shape or the clear vertex position that London was mentioning. And these are important because even in a liquid argon detector, we can't always see those protons attached to the electrons. And so this gives us more electron neutrinos, and it also makes us less dependent on the uncertainties associated with the nuclear effects, like Samantha was mentioning, that all of the details of how exactly protons are produced in these experiments, especially in liquid argon, is kind of new. And then I also served a 6-month term as MicroBooNE run coordinator. And so I was basically managing detector operations for MicroBooNE. And so it's fun to see inside LARTF again. So I was on call for 6 months for basically anything that happened. And then I would call somebody like Samantha or Lauren and say, oh, we're having this issue. Can you please help solve it? And then I also work on speeding up liquid argon reconstruction. And this is not only associated with MicroBooNE, but it's associated with how we get the information out of the wire readouts and how we process that data to send it and decide what happened, like what type of neutrino interaction it is. Before we can do that determination, we need to do a lot of processing of the wire readouts themselves. And this is actually the slowest part of our detector reconstruction. And as our detectors get bigger and bigger, we move towards, SBN, Icarus, DUNE. This limits MicroBooNE, and so we can't be limited by this as we move forward. And so I work on that as well.
Awesome. And Kevin, you talked a little bit about the theory work you did. If you want to share a little bit more about that and what you're currently working on.
Yeah. So one thing that's important that I don't work on because it scares me is related to what Samantha shared, and that is these neutrino nucleus cross sections. Not only is that something that needs to be studied in great detail in the experiments themselves, it's also something that challenges theorists like me. So a number of my coworkers in the theory group really focus on that, trying to calculate from a theoretical perspective what happens when a neutrino comes in and scatters off a nucleus of argon. This goes back to one of the questions during London's talk that was really insightful about what type of math is used. And that is pretty much the crux of what all theorists do. We sit around, we do math, and we try to talk to wonderful experimentalists about what they're looking at and how we can communicate between theory and experiment. And the math that's used by these people who study neutrino nucleus cross sections is very impressive. And it is kind of, if you keep learning things like calculus and linear algebra, it's kind of the next step along that path. You start to learn things like quantum mechanics. And then the tool that a lot of theorists use, and that's used for these calculations, is what we call quantum field theory. Don't let the name scare you. It's, like I said, it's kind of the next step along this path that you're probably on in learning different degrees of math. And so what that means in reality is that we write a lot of simulation code for computers. Some of my colleagues use supercomputers both at Fermilab and at Argonne National Lab, which is about a half hour away, to try to simulate what these interactions will look like and hopefully agree with what is seen in experiments like MicroBooNE. It's a really big challenge right now for current experiments. And then like Sophie was talking about, planning for the next steps, it's very important for these next experiments, especially things like DUNE.
Awesome. We have a question from Colin asking, are neutrinos a different type of matter since they have mass but pass right through the Earth? Do you want to take that one, Kevin?
Yes, they're different. So they're not like electrons or muons because they don't like to talk to electromagnetism. They're not like quarks. They don't like to talk strongly to each other. So neutrinos are special because the only force other than gravity, like London mentioned, other than gravity, the only force that neutrinos can interact with is this thing we call the weak nuclear interaction. It's called that because it's much weaker than the strong nuclear interaction and electromagnetism. So that's how they're special, and that's why they don't do anything for the most part traveling through the Earth.
Awesome. And, as people have questions, type them in the chat. I did have a question because as I'm looking through who's here, I'm seeing a lot of former Saturday morning physics students. So I'm going to ask a question on their behalf. What advice do you have for students that maybe want to pursue neutrino physics, knowing DUNE's going to be coming up and running, and that's going to be a long-term project, and we're going to need people that are interested in that, and want to study and get involved in neutrino physics. Lauren, do you want to start?
Yeah, I would say maybe a couple things. Follow your passion. If that passion leads you into neutrinos, great. We'll be happy to have you. If it leads you somewhere else, I'm sure that'll be cool too. Take the opportunities that you can to learn physics, math, statistics and probability, also very important, underrated in the general education system in general, in my opinion. And then another thing that I think is really helpful that I know I started learning way too late was computer programming. So if you have the opportunity to take like a solid class in any kind of computer programming, I would recommend that. And when you get the chance, usually sometime in the middle of your college years, find a professor who's doing this kind of research and see if you can get in with them for some summer research or research for credit during the semester or something like that. Because the best way to find out whether you really like this stuff and want to do it for a career is to actually go out and do it. I had really fantastic undergrad research experiences, and that's definitely a huge part of the reason why I'm here today. So.
Awesome. Samantha, you want to follow up?
Yeah, I would say also to Lauren's instance, I mean, doing research really helps you figure out if you like the subject or not. But I would say, like, don't be afraid if you get an internship that isn't neutrino physics, because research is a really different beast, and having sort of any experience with that will help you. So like, for instance, all of my undergraduate research was in optics and lasers, and I don't work with optics or lasers now. But a lot of the things I learned, like the analysis techniques and stuff, transferred really easily. Definitely start taking math and physics early. Statistics is a huge thing. I really wish I had taken more stats when I was in high school and undergrad. And programming, of course. There's lots of instances to teach yourself how to program. But what my program used to do, and I think people should do this regardless if your teachers make you do it or not, is take some of your homework problems and program them, because it forces you to start thinking, like, how do I take physics and put it into computer language, and then take what computers give me and put it into physics. Like, that was a huge, huge thing for me.
Awesome. Sophie?
I mean, I think that Samantha and Lauren just gave great responses. I don't know if I have that much to add, but I think doing physics in a classroom is really different than doing physics as a researcher. And you need all that classroom experience to build up your base of knowledge so that you're able to do research. But I think that having the experience doing research, like one doesn't necessarily translate to the other always. And so, like, the earlier that you can look for those opportunities, the more you'll get a sense for whether or not doing the research day to day is something that you really want to do. And I also think, like, as Samantha said, taking research opportunities, doing whatever you can, because you might be surprised. I had never heard of neutrinos until I took an undergrad position studying neutrinos, and now I just really enjoy doing it, and so now that's what I do. But if I hadn't taken something that surprised me, I wouldn't be here. And so I think just keeping an open mind like that is really important too.
Awesome. And Kevin, if you want to share a theorist spin on that.
I still had a path into this. No, the three of you all had excellent answers. The only thing I'll add is that it's never too late. Samantha and Lauren both mentioned statistics. I didn't take, I double majored in math and physics in undergrad, and I did not take a single statistics or probability class until I was in graduate school. And now it's like 95% of what I do. So you can teach an old dog new tricks. You can do research in one field and pivot to something different, even by the time you're in grad school. That's always an option. So find what you like. If you like research, awesome. And keep at it.
Awesome. And another one that came in as a direct question, and this is kind of a question I've been getting since we had a talk from main control room operators, when I believe the phrase was, if the booster isn't happy, nobody's happy. And so the question is for Sophie, how often do things like break? Like how often do you have to call somebody, say, hey, this isn't working? Like what's that kind of experience like?
Well, so for the booster, I mean, as someone who works in MicroBooNE operations, you don't control the beam. Like the beam is provided by the accelerator division and by people who work very hard in providing a consistent beam. And so your job as an experiment is to make sure that the experiment is running anytime that the beam is running. And so what that means is that when you're doing operations, if something breaks, you have to fix it very, very quickly, or you have to inform the accelerator division that, you know, this is really a big problem and we're not going to be able to take beam for some period of time. And so because it's, I mean, partially because it's expensive to run the beam in terms of money, but also in terms of just people, work and their time. And there are other things that need to be done on the accelerator side. And so, yeah, so when you're running an experiment, things have to be fixed quickly and, you know, in the span of hours, if possible. And so mostly things don't go wrong, I would say. Like for MicroBooNE, at least at the time when I was running operations, it was MicroBooNE had been running for several years. Many of the kinks were really worked out. The procedures were very clearly defined, but that doesn't mean that there aren't still issues sometimes. And so then, you know, you just have to be ready and, you know, can't put your phone on silent. You have to be prepared for somebody to call you any time of the night. And then you wake up and you say, oh, and then you have to evaluate, is this an issue that is a problem that needs me to call somebody else and wake them up? Or is it, you know, something that can wait until morning? And it doesn't happen that often, but when you do new things, it happens more often. So like when we did laser calibration runs, which is where we have a laser system that basically we can shoot a laser in MicroBooNE and measure how much the tracks curve due to ambient radiation. We had a lot more calls because that system hadn't been run since the previous summer. And so shifters were unfamiliar and there were, you know, just unexpected things happening that should have been expected. But mostly it's pretty smooth, I would say. And that's a testament to all the work that happened before and all the great procedures.
That's awesome.
That's an extra thing I'll say to be a neutrino physicist: be nice to your beam operators.
Absolutely. I mean, and I mean, I think from an analysis perspective too, it's really important, like when you, like basically to get more neutrinos, you have a very limited number of things you can do. You can increase your beam power, which is not up to you. you can increase the size of your detector, which London discussed the challenges of that, or you can do a better analysis to get more events out of your data and to lose fewer to your backgrounds or to recover ones that you would have discarded otherwise. And so it's really, that's the main challenge for us.
That's awesome. So we have a question from Gage. Do we have any indication of how neutrinos transition states, and how does that have an effect on how we go about detecting them?
So I guess I will venture with an answer first,
Okay.
and then everyone can correct me. So we do know that neutrinos oscillate, and we are aware of that happening. That was part of the solar neutrino problem, which was actually what earned the Nobel Prize in 2007. I don't remember. It's been a long time. But the idea was that when they first started looking for neutrinos that came from the sun, essentially they only detected a third of them. And so once they started looking for these other states, so looking for the muon and the tau-like neutrinos, then they found everything. So we are aware of the fact that they transition, but the idea is we don't honestly understand how the mass states are ordered. That's a very high-level theoretical thing. And we don't understand, but we also understand at this point how they oscillate. So we know with some probability that an electron neutrino is going to go into a muon neutrino with this formula, some equation. And the two main things in that equation that are super important are the distance from your neutrino source and the energy of your neutrinos. So if you're trying to detect, let's say, an excess of electron neutrinos in MicroBooNE, you want to make sure that the energy of the neutrinos you're looking at is the energy that you expect for that probability to be highest. And you also want to be at the same location where you expect that oscillation to, so you don't want to be right where the oscillation occurs. You might want to be a little bit downstream so to make sure that you're catching as many of those oscillations as possible.
That's great. Does anyone have anything they want to add?
Yeah, I'll just add a little bit that the reason that MicroBooNE and its forerunners are so exciting is because we think we have a pretty good idea of how the three neutrinos, the electron, the muon, and tau, can change between one another. And it was those forerunners, LSD and MiniBooNE, that seemed to see some additional transition beyond what we expected. So as a theorist, this means that there's something wrong with our theoretical understanding of these transitions. And MiniBooNE, LSD, and hopefully MicroBooNE are putting more cracks in that theoretical understanding that we can blow open and find, a sterile neutrino or other new physics with it.
That's really exciting. So as just to kind of wrap up for the session today, I just want to give you a chance to share something you're excited about that's coming up. Something I know London talked a little bit about possibly a paper being published soon, but just something that you're working on that you're excited about, you want to share with the people that are here with us today. Sophie, do you want to go first?
Yeah, I mean, I think that I don't want to be specific. I think it's a really exciting time for neutrino physics in general. There are so many new things to learn, and there are so many new exciting results that are coming out. I mean, on MicroBooNE, we hope to publish our first low energy excess results soon, but there are also, exciting results coming from other experiments, like the NOVA and the T2K experiments have both published these measurements of do neutrinos and antineutrinos oscillate differently, and they're a little bit in tension, and there's a question of what exactly is going on there and how can we resolve these in the short term or at all. There are the experiments searching for, as Kevin mentioned, neutrino-less double beta decay, and this Majorana nature of the neutrinos. I mean, there's so many open questions. And as London said, there's just a huge, great frontier of information that we have no idea about. And so I think that we're really starting to get some answers to these longstanding questions. And so it's a very exciting time.
Awesome. Lauren, do you want to go next?
Sure. I really agree with Sophie. There's a lot of super exciting stuff going on in the field that is going to kind of come together in the next, few years, and a lot of that is going to be really exciting. One of the things that I'm personally really excited about, and hopefully may work on after I graduate, is working with the SPND experiment, so the near detector in the Fermilab SPN program. That is really close to the source and is going to have really high statistics. So that's going to enable really precise measurements of relatively rare processes, and that should teach us a lot about neutrino nucleus interactions and possibly other kinds of exciting stuff. So I think that'll be really cool to see in the next few years.
Awesome. Kevin, do you want to go next?
Sure. Yeah, I'll throw a complete curveball. As exciting as all of the neutrino stuff is, one thing that I am particularly jazzed about is that a lot of these neutrino detectors can also function as dark matter detectors. So we haven't been talking about that today, but dark matter is one of the other big puzzles of particle physics. We don't know what it is, but we know it's all around us. And one thing that I and a number of my colleagues like to think about is, what if you could make dark matter in a neutrino beam? Similar to the explanation London gave about how protons hit a target and make neutrinos, well, there's the possibility that dark matter could be streaming out as well. And could that dark matter be traveling to MicroBooNE or SBND and scattering off the detector in some weird way, or decaying in there? And could these neutrino experiments not only be groundbreaking neutrino experiments, but also discover something completely different with dark matter? I think that'd be incredible.
Awesome. And Samantha?
There is so much to be excited for right now. I think I'm really excited to see the fruition of all the work, like seeing my friends having worked so hard for so long to finally see our hard work come to fruition is so exciting, and to share that with the world. It's also exciting, with DUNE coming online, one of the first neutrino experiments that did research was Arthur McDonald's. That was part of the solar neutrino that I mentioned before. It was actually in Lead, South Dakota. It's in the same exact tunnel where they're going to start building DUNE. And so just to see this story kind of have this arc and ending, I don't know, it's so exciting to think about how, they first postulated this particle 100 years ago and being we don't know if it actually exists, but maybe. And now we're building high-end detectors to do it. It's exciting. I think it's really exciting to also see the outcome of neutrino-less double beta decay, because I think that's a really long-standing issue that we don't understand yet. And of course, interesting to see what kind of physics we're going to discover along the way. You just never know. So that's always really exciting.
That's awesome. And I just want to thank our speaker. I want to thank our panelists for being here and sharing this awesome information and answering our questions. I want to thank everyone being here on, whether it's a Sunday afternoon in your time zone or an evening or early morning. It's really cool to be able to connect with people from all over in this virtual setting. So Ask a Scientist is going to take a pause over the summer. We'll be back in September, but there will be an announcement coming out soon about what we're doing for our summer science series. So thank you all so much for being here. I learned a ton. This was great. Thank you so much, and enjoy the rest of, like you said, your day, evening, morning, whatever time it happens to be where you're at. Thanks,
Thank
everyone.
you for organizing.
Thanks.
Thank you.
Bye-bye.
Bye.